Yes, we can see your presentation.
Thank you
Please, the floor is yours.
Thank you very much, Sergey, and thank you very much for the invitation. And I also thank you. I would like to also to thank Dmitry to give me very nice introduction to what I will be talking about in a moment, because well, there will be a lot of common points, and actually, it's nice that you have already introduced. I mean, the basics of the topic. So this is like a development of the, follow-up, but focused on molecular interactions, which are, I would say, so the calculations of molecular interactions is quite different from other quantum chemical properties.
Excuse me, Piotr, can you speak a bit loudly, or
Okay, just a second. Maybe I should.
The sound is not so loud.
Just a second. I will try to maybe change a microphone somehow. 1 second. 1 second. Okay. Maybe our.
Yes. So just to fix to hear better.
How about now? Is it better?
About the same. About the
same.
Maybe a little bit better, but.
Audio settings. Okay. I can increase the input level in the mic. Is it better?
It's much better.
Okay. It was
okay.
Good solution. Thank you. Okay, so as I say, actually, I'll be giving like a follow-up talk on quantum chemistry still, but as I say, focus on different matter. And I'm Piotr Żuchowski, so I come from Toruń, which is this part of Poland. It's like central north. And it's a city known to be a hometown of Nicolaus Copernicus. So it's not a big city, it's 200,000 people, but it's a good university. Institute of Physics is in the middle of the city, and we have quite strong representation of group in quantum chemistry, but also in spectroscopy. So I highly recommend to come at some point to our city. And I'm also a working group leader for working group 1 in COST, which is molecular interactions. So the method is the working group is focused on method development and some kind of bringing new applications to COST, let's say. Bringing them for new applications in COST. So molecular interactions are very important, and I will try to start with some introduction, which is on applications of that. In what areas of physics you can encounter molecular interactions, and why one needs accurate calculations. Then I will talk about supramolecular calculations, which actually Dmitry started at the end of his lecture. And I will talk shortly about symmetry adaptive perturbation theory, which is alternative method for supramolecular method for the calculation of interaction energies. And I will briefly maybe mention the dipole moment surfaces, which is, maybe it's not so popular, but it's worth to know that this area of molecular interactions is developing, and soon maybe it will become more popular. Okay, so I will start with something very simple, with the most simple quantum chemical system, nearly the most simple quantum chemical system, which is helium dimer. So for helium dimer, actually, there are a number of experiments which are extremely important. The system is so small so that we can actually calculate the interaction energies for that system. Generally, the energies for helium dimer extremely accurately. Actually, the accuracy of calculations is so high. So actually, if you want to measure some experimental quantity related to properties of helium, like for example, virial coefficient. So basically, you imagine you have when you have
2601 mi aldın?
when we have, for example, noble gas. I mean, real gas actually it differs from van der Waals gas. Yes, as you know, if you start to compress the gas, then atoms start to repel, for example, and then there are needs to. I mean, so basically, new parameters to the models are needed to be introduced. So basically, in order to describe this deviation of the gas from reality, you have to, for example, define the virial series. And as far as interaction energies are concerned for helium dimer, then this is actually the I wanted to show something like this is the very end of the what is currently possible with quantum chemistry method, which is super highly accurate results. So for that kind of system, it was I mean, in Jeziorski group a couple of years ago, they, for example, managed to calculate interaction energy, which is like at Born-Oppenheimer level, which does include some correction beyond Born-Oppenheimer, which does include some relativistic and QED corrections, because they want to make some specific calculations for which are designed for making the I mean like benchmarks for helium to which is important for metrology, right? So for some system, actually, I want to stress that the accuracy of calculation is so high that they are more credible than theory. And actually, you can tune, for example, your I mean, like you basically, in order to learn something, how to tune your system, I mean, how to use it in metrology, it's better to have calculations than actually measurements. So this is actually some kind of very interesting thing is, for example, the size of the helium dimer. So size of the helium dimer, actually, helium dimer is very shallow potential well, which actually conveniently it's measured. I mean, people give usually the binding energy of helium in kelvins. So the binding energy for, I mean, the well depth for actually this is not correct what I plotted here. So the well depth in helium dimer is about 10 Kelvin, but helium, on the other hand, is so light that the first vibration, the only bound state in helium is what I plotted here is very, I mean, like it's nearly, I mean, it's very close to the dissociation limit. So the binding energy of, so D0 actually should be like the difference between threshold and this orange line. So what is plotted here is actually the zero energy point, right? Energy. So basically, this is like the dissociation energy of helium. I wanted to show how it's sensitive to very tiny effects like retardation, like QED effects, and beyond Born-Oppenheimer. So sometimes, yes, I mean, you have to. I mean, you have to be very careful in the calculations of interaction energies. But actually, for some system, actually, the accuracy can be astonishingly high, and probably I mean, not probably. I mean, for sure, the helium dimer is like the system for which this accuracy can be achieved at very high level. So those are like examples. So experimental measurements for virial coefficients are in the red, and the theoretical curve is here, right? So for theory, actually, it's very difficult to put the put the uncertainty, yes, because I mean, you can put only systematic error. I mean, systematic error, no statistical errors. But I mean, in order to to provide sensible error bounds, then you have to carefully study each step of calculation of Born-Oppenheimer curve, relativity curves, QED, etc. So each of these terms needs to be like, you have to analyze to what extent it's you can be wrong, basically, right? And this is usually difficult. And those here actually we have some properties which are important in the gas phase calculations of molecular interactions. And so basically it's possible nowadays to address those coefficients, which are by just using theory, not only for helium dimer, but also for heavier atoms like argon, like neon, or H2, or nitrogen. So basically, what is currently quite nicely developing is like metrology based on quantum chemistry calculations, right? So of course, actually, only helium is for. I mean, for helium, actually, it's possible to address the accuracy with very high demands. It's not possible yet for argon or neon, for example, or for nitrogen, but it's also quite good. Another example, which I wanted to show you, is how the molecular interactions and calculations of potential energy curves this time from quantum chemistry calculation can help explaining some physical phenomena, for example, in this case, related to quantum scattering. So here there was one of the most interesting topics in atomic physics is something which is called ultra cold physics. So physics of where atoms are at very low temperatures, and at very low temperatures they collide with very small kinetic energies. So if you think about quantum and classical scattering, so classical scattering usually is when you have high velocities and heavy colliding species, whereas if systems are light and they collide very slowly, then you should see some quantum phenomena. And indeed, one of these phenomena is, for example, shape resonance. So basically, if you collide atoms with very low kinetic energy, so here at this figure from paper of Edna Revicius, you can see the reaction rate and collision energy. So collision energy actually, whenever it's lower and lower, then you see some features in it which can be attributed to quasi-bound state. So basically, when your Born-Oppenheimer potential, actually, when you add to that potential the centrifugal barrier, then you see that for some very low quantum numbers L, you see kind of there is a place for confinement which can support the bound states. And those bound states, when your collision energy equals to the quasi-bound state energy, then you see the shape resonance, which is that feature here. And by the way, you can think what kind of reaction you have here. So those are collisions of metastable helium with hydrogen. And metastable helium is helium with extremely high energy. So it's basically excited helium. So the excitation energy of metastable helium is much higher than ionization energy of hydrogen. So whenever those two collide, you see the production of electron and ions, and you simply record them, right? So that's why we can call this kind of collision a chemical reaction. Yes, it's like auto-ionization reaction. So okay, actually it was possible then to explain the origin of this shape resonances with high-level ab initio calculations. That was possible. So basically, a couple of years ago with Ed, actually we explained the progression of shape resonances in various isotopic species. So instead of not only H2, but also we studied HD or D2, and basically those resonances, they shift once you change the hydrogen molecule to something more complex, to something like D2 analog or HD. So basically the resonances shift. And with potential energy surfaces which we obtain, so basically they are not they are not, I mean, initially we had some like not accurately enough potentials, which we needed to tune to the experiment, but clearly actually just one tuning, so this is the blue line, allows you to explain the resonances in details actually. So when you tune with wrong factor, then you predict some artificial resonance here, which is basically because your predicted potential is not good enough. So I mean, later on, this experiment was refined, and actually much more accurate calculations were done with theory. So basically, this is actually a kind of composite scheme which we very often apply for your in supermolecular approach, which I will show you in a moment. So basically, it's possible to calculate like super accurate supermolecular calculations for one method. However, actually, you need something more accurate. So, but the basis sets doesn't allow you to do super expensive calculations. So you take some smaller basis set, and you hope that this, if you calculate it with smaller basis set, then still actually it will improve your actual result. And indeed, that sometimes works. So basically, our composite potential, which actually encompasses a couple cluster at triple levels, calculated up to something like augmented 7 zeta basis set with CI, I mean full CI, which is essentially in this case couple cluster with quadruples at triple zeta level, with some flexibility corrections applied to so which accounts for the motion of hydrogen in the complex. So that actually reproduces correctly all the resonances, and so we were able to like provide full ab initio explanation of those shape resonance in cold collisions. But this is not the only important application in context of gas phase phenomena. So molecular interactions are also important in astrochemistry. So this is like since in COST, actually in COSI, we have working group 1 and working group 5, working to a large extent on similar topics. For example, actually simple application, I mean, I wouldn't say simple, but quite common application of ab initio methods is to obtain potential energy surfaces on top of which you calculate collision rates. And those collision rates are extremely important for astronomers. So you can nowadays see nice collaborations between ab initio people and astronomers. Or so basically the goal is to provide collision rates for models in astronomy. So nowadays, actually, what appears is like we have more and more complex molecules and heavy colliders, not only for so usually the most common element in the universe is helium, so and hydrogen. So in most cases, those calculations are basically they focus on collisions of various molecules, also quite big, like for example some heterocyclic molecules with hydrogen or helium. Because it's like you discover the molecule in the space, and then you want to model the environment in which it was discovered. Then you need collision rates with helium and hydrogen to basically, for example, calculate the abundance of that method, of that molecule. Oh. But also what is nowadays actually in the era of James Webb Telescope becomes more and more important is like you also can follow very accurately, for example, model and study accurately the molecules in comets, for example. For comets, actually, not only hydrogen, it's the collider, but also CO or water molecule. And those collisions are also can be very important, right? Yes, and yes, so this is like a paper which actually suggested that indeed in next years, actually so the paper was published last year. So that was like a work from Hydron people Laurent Wiesenfeld, who is actually molecular physicist. So he is doing scattering of molecules in the universe. So basically, what will become important in the near future is also like potentials for molecules which are perturbed by hydrogen, CO2, N2. Then actually from potentials, actually it's possible to extract the models, for example, to improve the models and guess the conditions which are, for example, at exoplanets, right? So this is actually not quite intuitive, but indeed, that's the future. And more recently, also some features of in collisions of atoms, they can be also attributed to so basically changes of dipole moment while the molecules collide. So those things are. I will not maybe elaborate much on that, but so basically, if complex is momentarily close to each other, so if for example, two CO2 molecules are close to each other, then they can absorb the photon, and you can see such features basically and analyze the spectra from exoplanets, and you can guess again the concentration of exotic molecules, for example, at exoplanets. So this is, for example, the simplest way of discovering oxygen at exoplanets. Yes, it's because oxygen itself is not active spectroscopically, then only complex will be possible to observe. But okay. So in gas phase, in the context of gas phase, potential energy surfaces are important, but it's not only that. Actually, it's also, of course, explaining the spectroscopy of like infrared or Raman spectroscopy in liquids. It's also one of the big problem. So basically, in order to model spectra in solutions, actually, of course, you can use some you can treat your environment like an average dielectric environment with some specific electric constant, but sometimes you need to explicitly simulate molecules interacting with something which is actually vibrating, for example. In that case, you need some explicit solvent calculations, and indeed, there is also progress in that. So, yet another example from soft matter is, for example, biophysics. So there was a very nice paper of explaining why you need a very accurate quantum chemistry method in order to reproduce DNA helix, for example, right? That was actually quite long ago, 2008. And people in the meantime, actually, they learn how to deal with DFT calculations, reproducing dispersion. So I'll talk on that. But also one of the most important also industrial applications of calculations of intermolecular interactions is, for example, predicting of crystal structure. So basically, this is a big pharma actually wants sometimes from quantum chemists to predict what will be the structure of given crystal. And imagine you have molecule which has a lot of very flexible modes. So basically, molecular interactions are hard to predict, but the molecule also can bend, can twist very easily. So the crystal can have a lot of polymorphs. So actually, it's very hard to address this. To properly reproduce the to say in what conditions to what structure given molecule will crystallize. This is actually a very famous competition, which is called like a crystal structure prediction assessment. I don't remember exactly the abbreviation, but basically there is every couple of years, a community actually tries to predict crystal structure of something which was not predicted yet, just from first principles. And later on, that kind of comparison is made for all groups in the competition. So last competition was in 2000, I think 2 years ago. So that was 7th test. So for those who are interested in it, then I recommend to look for it. But okay, let's start now. So once I hope I convinced you how important it is to know accurately the potential energy surfaces and how to generally, I mean, that it makes, indeed, it is a big effort, and but at the same time, there is a number of problems which is basically, there is a number of problems in physics which needs to be addressed, and this is the only tool with which they can be addressed. So, how we calculate molecular interaction energies. So this is exactly what Dmytro told you at the end of his talk. So the concept is called simply supermolecular method. I mean, I'm not sure if he used that name specifically, maybe not. It's not so important. I mean, some people don't use this name, but it's irrelevant. But the method is very simple indeed. So, it's simply from the very definition of interaction energy, you have to subtract the energy of complex from energy of monomer A and monomer B, so the constituents of the complex, and you should have interaction energy. This is a very simple idea, actually. Whatever program, quantum chemistry program you have, you can imagine you can use it with, right? But there are problems with that, and already one of the issues was addressed by Dmytro, and this was BCC, which is called basis set superposition error. So I'll repeat that because it's very important. So basically, imagine that you have basis sets. Basis sets are Gaussians, and if you have a complex, so basically, if A and B are close to each other, they in some sense borrow the basis set function from each other. So you can say that the basis set of A is better within the complex when B is close rather than when they are isolated. So it's not good because you will lack some kind of systematicity here, right? So basically, essentially, you can say that energy of A when B is close should be lower compared to the situation where it's isolated because it has bigger basis set, because basis set is finite. So variational principle tells us that, roughly speaking, the bigger basis set, the lower the result should be. And indeed, I mean, that was quite early discovered by Boyce and Bernardi, and there is a very well established way of removing that error, which is called counterpoise correction. Indeed, you take the same basis set for each atom. So you do a trick, basically. Whenever you calculate monomer A energy, then you calculate it with the basis set of dimer, actually, and you keep the atoms. So basically, you pretend that there is no charge on atom B. There is simply the basis set. That's how you can remove that basis set. This is extremely important. Otherwise, your results will make no sense. Yes, and the devil is in details, right? So the problem is like, okay, what are the order of magnitude of these numbers here? I will show you in a moment one nice example. And then actually, when you realize what is the difference in orders of magnitude between left part and right part of the equation, then you will think, okay, what happens if there are errors in EAB, EA, and EB? If there are errors, then you realize that the E int is very fragile with respect to the errors. And then do you infinite? Okay, so let's take one example, which will be formaldehyde dimer. So I've took some augmented double zeta, small basis set in Hartree-Fock, just to make you aware that the subtraction is not so easy. So this is the dimer energy, this is monomer A energy, and monomer B energy. And this is the interaction energy. So you see what? This is the hundreds of Hartree. Hartree is a huge unit. And this is 6 orders of magnitude smaller quantity. So basically, you need to be very accurate in calculating all these three components, because you subtract basically. You have huge number here, huge number here, huge number here, and the result of subtraction is here. Essentially, you lose accuracy when you subtract those numbers. So here you have so basically you essentially lose something like 5 significant digits, right? Because you have 0.04. So basically you have zeros here. And so basically if you add those two numbers, then you will get something like 227.77, and only at the fifth significant digit there will be difference. So basically you need to be very careful when you do the subtraction. So this is Hartree-Fock energy. So okay, you say Hartree-Fock is a poor method. So how it okay, that's also very important. So to show you the effect of BSCC, actually, I don't have the bare number, which actually, well, you can actually figure it out, but see, this is actually the difference of the basis of the calculation. I did Hartree-Fock calculation with just one monomer, so without this ghost function. So roughly speaking, those are the numbers which you would have if you don't do counterpoise correction. So this is like, of course, those numbers are nearly identical. So those monomers are slightly different because it's like geometry optimization slightly distorts one of the monomers. So, but their energy is like equal to 4 digits after comma. But you see, actually, okay, monomer energies here. You see, you can reproduce only 2 significant digits. So basically, the error of calculating monomer is actually comparable to the error of the interaction energy. This is why you have to do the counterpoise correction. So, as I say, these quantities are very, very sensitive to details of calculations, right? So, for couple clusters, this is a correlated method which was basically discussed. So, for a couple cluster, you see those numbers are vastly different. Actually, 1 Hartree is a lot. I mean, just to make you aware that it's so formaldehyde molecule in couple cluster is just is half Hartree more than in Hartree-Fock, but half Hartree is a lot. So basically, this is the interaction energy at couple cluster level, and monomer center basis set calculations give you roughly the same error. So basically, energy of monomer is again valid up to 5 significant digits. There is a difference of 6 significant digits, which is actually comparable to our interaction energy. Now, okay, let's take CISD, which is variational method, it's configuration interaction. It's configuration interaction gives you completely wrong result. Okay, so basically it gives you positive energy compared to Hartree-Fock. I mean, just okay. I mean, maybe I should somehow prove you that indeed this is a good energy, but just believe me that for the moment that couple cluster is like a gold standard method for quantum chemistry. People very often use that phrase. It's gold standard method. So indeed, for systems like formaldehyde dimer, you can really believe to couple cluster at triple or double zeta. So why CISD gives completely wrong energy? So this is actually a very important demand from quantum chemistry method you use for molecular interactions. The method needs to be something which people call size consistent. If you open the book of quantum chemistry, it will turn out that some methods actually they are quite good in describing correlation energy, but not at long range. Basically, at long range they are completely wrong, and it's not so simple to explain why it's completely wrong. You have to be aware that methods like CISD or multi-reference CISD or multi-configurational CAS-SEF, they're in general not size consistent. So the method with which you use for calculation of interaction energy must be size consistent, and this is actually absolutely crucial. Okay, so this is again triple zeta, and I wanted to show you triple zeta quality calculations for couple cluster. The difference was not that much bigger compared to double zeta. And you see that if you increase the basis set for triple zeta level, you reproduce more and more significant digits. And this is actually true. So the bigger and bigger basis set is, smaller BSCC is. So basically, if you extrapolate your results to basis set limit, then BSCC is no longer an issue. So this is actually quite logical, because BSCC originates because of the fact that you truncate your basis set, right? So if your basis set is potentially infinite, there should be no issue with that. But of course, if you want very accurate interaction energy, then triple zeta is of course not enough. Okay, so just a summary on supermolecular calculations. Yes, you won't have to be very careful in such calculations. You have to also, I did mention that, you have to set very tight thresholds for such number, right? So you have to reproduce, I mean, STF is like a method in which you convert your result up until some threshold where your energy doesn't change. So your threshold in that case needs to be very small. I mean, smaller than the accuracy of interaction energy you need, right? So typically the default is 10 to the minus 6. Then of course you see that 5 is like 10 to the minus 5 is like 5 orders magnitudes are gone basically when you subtract the molecules, right? So you need to increase your accuracy by 2 or 3 more orders of magnitude. Then counterpoise correction is essential, and you can use it only with size consistent method, which is like couple cluster MP2, not with MRCI, not with, you have to be careful with open shell couple cluster, by the way. Also, F12 calculations, F12 method is not like, in some variants, it's not fully size consistent, which is sometimes not known, but the method is quite popular. Yes, and then also from supermolecular calculation, you get just one number, interaction energy, and how to understand it. And there are some decomposition schemes which divide interaction energy into some components, which help you sometimes to attribute and somehow understand the interaction. But it's not always the case. I mean, this is actually a non-unique procedure, not always available. So I wanted to show you something else. Okay, important issues also about the DFT. So DFT actually is size consistent for sure, but DFT doesn't have dispersion interaction. So in past years, actually past 20 years, so people like Stefan Grimme or Alex Tkachenko, they basically introduce a lot of schemes which fix the problem of dispersion in DFT. So what is the dispersion? The dispersion is like a interaction, is like the correlation between monomer A and B. So basically, if you imagine that your electrons in, let's say you have atom, will go to one corner of the, well, to one side of the atom, then the other atom, to some extent, feels that there is a dipole there, and it's the other electron tries to orient in such way that this energy is minimal of the interaction of two dipoles. So this is actually, this effect is called dispersion. So dispersion is essentially electronic correlation. That's why this dispersion cannot be recovered by Hartree-Fock calculations, and it's like completely nothing there. So Hartree-Fock is no dispersion, doesn't have any dispersion. Some of this dispersion is introduced in DFT, but it's like not very universal, because in every functional is different. I mean, the perturbation analysis, which I will talk in a moment about, will help us to understand the dispersion properly. And one of the very important features of the dispersion, which is like if you describe two atoms, then dispersion energy should go to the infinity it has very well understandable, it has understandable asymptotic. So basically it should go as r to the minus 6. And this is the result was actually known from 1930s. So basically this is like the dispersion energy should look like. It should be finite at 0 because it's correlation energy. And it should go to 0 as r to the minus 6. And what's in between, then as actually various methods struggle with that, right? Especially DFT. Okay. So DFT can be corrected with some atomistic simple models, like you simply add to each atom r to the minus 6 term multiplied by some damping. So this is for example, a figure from QChem website. So with some proper empirical tuning, you can get those parameters, and then you can make your DFT working. And that's actually makes those methods extremely popular, but also very efficient. So people use this DFT fixed with fixed dispersion massively, and in most cases it's working well. However, actually, if you look at the interaction energy for this is some simple system, I think something like argon dimer in various DFT models, then you can see there is a orders of magnitude difference between among various functionals. So this is actually quite crazy. So you have to be very aware of what functional to use with what parameters, so that those parameters for empirical dispersion, actually, they are tailored to each functional separately. You cannot use P3-lib parameters with scan, for example, or PBE0. They are completely different parameters. Without dispersion, this is how would DNA helix looks like. So people actually, nowadays, actually, I think the structure of DNA helix is properly reproduced because, really, it's not, DFT doesn't reproduce this long range correlation, especially, which makes this, like chaos between, like distant pairs here, right? As opposed to order. Okay, so now I would like to talk to you about symmetry of the perturbation theory, which is like how you can use perturbation theory for calculations of interaction energies. I have about 15 minutes. I should use it. So this is completely different philosophy. So basically in perturbation theory, you can say what is the perturbation there, but instead you have monomer A and monomer B, and what's between you treat as perturbation. And this is actually small perturbation you can think about. Especially it's small when your monomers are far apart, let's say, not at the interactive wall, right? So you use perturbation theory known from quantum mechanics to expand the energy and wave function. There is only one conceptual problem, is that what is your wave function should be like. So you start your energy, there should be something like 0th order approximation to the wave function, which in this case is not so easy to invent, because you would like to use something like you have a product of A and B monomers, but the product is not correct, basically, because it doesn't describe properly the permutational symmetry of the complex, actually. So electrons within A, they can really, they can basically, the wave function is how to say, it's anti-symmetric to the permutation of all electrons within A and B separately, but not between those two. So basically you have to invent the procedure to enforce symmetry, which treats all electrons on equal footing. So basically in that case you can replace the energy from A to monomer B, and only in that case you can reproduce one of the key components of the interaction energies, which is called exchange energy. So here I have some short summary of advantages and disadvantages of supermolecular and SAPT method. So of course, actually in perturbation theory, actually you have no BCC problems. So you do not lose accuracy because you calculate your interaction energy directly without any subtraction. This is very nice. Then actually you don't need the dimer wave function. You just need the monomer wave functions. That's also very nice because you have, I mean, you solve Schrödinger equation for n. So for helium dimer, you solve the Schrödinger equation for 2 electrons, not for 4 electrons. And then you also, as I will show you, actually provides some analysis tools for what is in actually your interaction energy, what is its origin, basically, what are the physical effects behind it. So basically, there is no such thing in case of supermolecular calculation. However, actually, of course, supermolecular calculation, one big calculation is that there are many quantum chemistry programs with that, as opposed to symmetry adapted perturbation theory. And it's high quality codes, actually, they're extremely well optimized, which allows you to calculate indeed very quickly interaction energies without any problems. So first order of the interaction energy, roughly speaking, actually is very closely related to physics and how those effects can be explained. So basically, it's particularly worth to mention. So like first order actually reproduces the electrostatic energy. It's simply this integral here. This is the integral over density of A, density of B, and the distance between them. So this is actually the electrostatic energy, very intuitive picture, very classical. It's like interaction of two clouds of electrons, two charged clouds. Second order actually corresponds to dispersion energy, there is a formula which is very complex on that. So you just illustrate it somehow. But also induction energies reproduced in the second order. So induction is like you have dipole, which, for example, you have water and helium. So water polarizes helium. And helium now actually has this induced dipole moment, which interacts with water. So actually that's something which is included in the induction energy. And normally in SAPT theory, you get your interaction energy as sum of terms up to the second order and beyond, but beyond, I'll comment on that now. And then you can actually use those, I mean, there are various flavors of SAPT, and they depend on how you calculated the monomer or density. So most popular nowadays is SAPT, parenthesis DFT, in which monomers you calculate from DFT, which means that you have, for example, to some extent, the dynamic correlation is there, right? So they include correlation. But in contrast to conventional DFT, the dispersion, for example, is calculated properly. Other choices is something which is called SAPT-0. So it's like very cheap SAPT, cheaper than SAPT DFT. SAPT-0 means this is based on Hartree-Fock-Slater determinants. And roughly speaking, its quality is comparable to MP2 quality. So basically, it does include something like dispersion at MP2 level, roughly speaking. SAPT2, something which is equivalent to MP4, roughly speaking. And there are also more complex models used and implemented. I will show you how they are implemented. So this is a picture, actually. So the story is like, for many years, SAPT was like a Polish invention and developed by Bogumił Jeziorski and Krzysztof Szalewicz. And there is this program which is called SAPT 2020 nowadays. It's free of charge. Based on ORCA, you can calculate interaction energy for fairly big systems. Alternative program with very good SAPT implementation is Psi4. There is a free of charge Python-based quantum chemistry program, also very efficient. So at some point, David Sherrill and his group implemented SAPT methodology into Psi4 package, and they made it use formula. I mean, it's like fantastically easy to use. So basically, well, okay, a couple of years ago, it was really painful to calculate the interaction energy with something like, SAPT program. But nowadays it's very, very simple. So there is like a zoo of SAPT methods and flavors with some increasing accuracy, let's say. Right. So one of the disadvantages maybe of that method is that there is indeed, you have to be aware of what you add, and you have to follow the recommendation of people who did a lot of tests, because the main problem with SAPT for the moment is what's beyond second order. But SAPT DFT just focus on that, so it's really highly accurate. It's actually with accuracy comparable to couple cluster for many systems. Works for tens of atoms, and as I said, this is okay. It's also implemented in MolPro. So yes, and you can use it actually with any functional, right? So the most recommended one is PB0 with asymptotic corrections. The ugly side and the drawback, and this is actually, we are working on that right now to address those problems, is what's beyond third order. So you usually add something which is from Hartree-Fock. If you want to, so perturbation theory diverges. And sometimes it diverges quite badly. For example, if you have strongly polarizable systems. So one remedy is that instead of third order, you calculate something like, so basically at Hartree-Fock level, induction is reproduced to infinite order. So basically, and you also are able to reproduce Hartree-Fock up to the second order. So you basically define something which is called the delta Hartree-Fock, which is like a difference between what should be beyond second order, second order in SAPT, and you calculate it with supermolecular method. It's not very nice, but it's working quite well. But at the moment, it's like the bottleneck of SAPT for very big systems, and in future, I hope we will remove it. Some applications of that. It's interesting to know that Krzysztof Szalewicz actually developed a very nice program which automatically generates quite complex potential energy surfaces between systems. We used it in astrochemical context for calculations of rates, so those are systems which we tried. But also it can be used for some like crystal structure prediction, so it's a very efficient program. And there are developments in SAPT for multi-reference system, but this is like still, very fresh, and a lot of test system needs to be still done. So I developed, like for example, the case of spin splittings, like oxygen dimer. My colleagues, for example, they were developing like systems SAPT based on CAS-SCF, which allows you, for example, to calculate interaction energies for dissociating molecules. Very important application, I would say. Those are the biggest system for which SAPT was used so far. This is HIV protease complex. At some point it was done by David Sherrill. So with that, actually, you can actually understand much better what happens actually as far as the mechanism of the interaction is concerned. And the calculation is also quite simple. So this is an input for Psi4. Psi4 can be also used as a Python module, and you can simply, there are methods and objects. So basically there's a method of calculating the interaction energy. So it's very easy for method development. So this is water dimer in the minimum. And this is simple output. So this is SAPT 0 calculation. You can then, so this is your interaction energy at Hartree-Fock level, for example, and at SAPT 0 level. You can see, for example, that a lot of interaction is basically electrostatic. So this is typical van der Waals system. There is some minor exchange, and induction is also quite important. It cancels out with exchange induction. Well, there is not that much dispersion, and that's in water dimer, as you can see, yes, compared to electrostatics. Then if you use correlated SAPT 2, which corresponds roughly to MP4, then you can see that, okay, SAPT 2, the interaction energy, okay, the interaction is shallower compared to SAPT 0, because Intramonomer correlation, for example, changed exchange energy. So now actually there is less repulsion than actually it's at the Hartree-Fock level. So basically those things can be extracted from output and processed. And you can ask why to decompose systems. Actually, it's actually very important nowadays when chemistry becomes like data science. So what is actually very popular nowadays and very useful, it's like people are composing benchmarks data sets. So whenever you have a new method, test it on some representative system, not a random choice, which is not a random choice, but it needs to be somehow nicely composed of, there should be a variety of various interactions of types of interactions in your set. It's not like you have, you imagine that you have 100 systems and you can have, for example, only noble gases. It doesn't make sense. So you can assess those diversity, but by picking, basically by plotting, for example, something which is like ternary diagrams. So basically you basically illustrate the fraction of each component by a point on a triangle. And this is also point on triangle, depending whether electrostatic is positive or negative. So basically here, for example, you can see that data set S66 of Pavel Hobza is not as diverse, I mean, is not as properly representative for induction forces, for example, whereas SSI side-side interaction for proteins, for example, is very representative, right? So it can help you, for example, to make a categories of dimers, to put them into given, categories which can be quantified, right? It's not like, okay, I have intuition that water dimer is similar to H2S, H2S. You have numbers to make this, assignment somehow automatically. So that's very good for making various, quantification of systems. So here is the example of data set of Jan Rzezak from Prague, who composed this NCI atlas, no covalent atlas. So for various tests, for example, you want to learn some, you want to develop some machine learning model for molecular interactions. There is a ready data set there. Just run the calculation. And in order to make that proper data set, in that case, you have to, you can basically quantify. So the icon here, for example, represents actually to what is the fraction of dispersion, induction, or electrostatics in given system. So that's why they are important. Okay, maybe I will skip this. Just wanted to make an announcement that we also developed sub-theory for properties, but just it was published this year. So you can also describe, for example, dipole moments. So imagine that you have two non-polar molecules. You can describe how the dipole moment will induce between those systems. And that's much harder calculation than interaction energy, but also possible. So just a short summary. It just I will refer you to what I was previously talking. Supermolecular calculations, you have to be very careful with your calculations, and you have to be aware of subtractions which are there. Subcalculations are alternative method in which you calculate molecular interactions with, like you can compose the interaction energy from components, and you don't have the BSCC. And it's actually, yes, okay, I didn't announce properly, but here actually, if you're interested in and you want to learn quickly and make use of SAPT, then I recommend you Psy4 quantum chemistry code, which is free of charge. It's very easy to install in a Linux system with Conda package manager, and allows for, I mean, it's a great educational tool, but also, I mean, real like quantum chemistry tool. Okay, so I think I'm done. So at the end, I want to thank my collaborators and sponsors. And okay, I'm ready for any questions if there are any.
Thank you very much. Let's thank our speaker. And now we open the session for questions. Please, who have questions? Probably some questions in Zoom. I think participants are thinking about questions, and I would like to ask about such interesting figure where you show a comparison of DNA chain.
yeah.
Double chain. In one case, we have double helix, and in other case, we do not have helix because, as I understood, the dispersion interactions are not included to the calculation. Am I right?
Yes. So actually, this is actually very important thing. Is basically when you have, if you have, aromatic rings, they basically stuck together, right? This is actually it's the same in graphite, for example, right?
Yeah.
So stacking of aromatic rings is possible because of dispersion. And essentially you have, it's very well known that you have hydrogen bonds in the DNA helix, right? Between bases, but also you have stacking. So in DFT level, you have properly reproduced hydrogen bond, but you don't reproduce stacking. And because of lack of stacking, you see there is no structure in this helix.
And I also have a question about electrostatic interaction between phosphate groups. We have -1. We have -1 charge.
Yes.
And do we have this charge in the case of this calculation?
Yes, I think DFT is quite good for electrostatic interaction, by the way. Yes, so normally you can use DFT actually for, for something like water or for something strongly polar interacting dipoles, let's say, or even if you have positive charges, then DFT is quite good. I think DFT is not good for negative charges, if I remember correctly. And but for ionic species, I think it's quite good.
Well, but phosphate group is negatively charged.
Okay. In that case, I don't know exactly.
Well, I mean,
because ions, negative ions are kind of diffused, right? So I would say, okay, long range forces in this case is like you have the induction interactions are probably quite okay, but I'm not sure about if I remember correctly, then.
Well, I just, for me, it's very interesting because as I see, we have double helix, and as I understand, there is no water molecules around, there is no counter ions, and for me, it's a big surprise that we obtain such a real big conformation of DNA. Looks like big conformation, B form, without any hydration shell.
Okay.
So for me, it's
maybe you should use some kind of SAPT tool to analyze it better. Yeah, although it's kind of big system, but
maybe some algorithm compensates this. I don't know.
It's also possible. Yes, you may have some error cancellation.